This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon. When you're ready, we'll make a start. So, if you do want to contact the student rep, Simona's email is on LMS. Okay, so email her. I'm aware that the lecture capture only recorded the audio for the lecture on Tuesday. I don't know what happened there. When I just plugged into the system now, originally it said that it wasn't connected. Then I flicked it to VGA and back to HDMI, and now it's connected. So hopefully it will be recording today's lecture properly. This system is all automated, right? I don't do anything, I just plug in, right? So I don't know what changed on Tuesday and I don't know what changed now, but flicking to VGA apparently connects it. So what I'll do is quickly try to go over some of the handwritten stuff, so that there's a record of that, assuming that it's being recorded now. So we looked at this result, okay, about bounded inputs always leading to bounded outputs, provided the impulse response is absolutely integrable. Okay, and we saw that, in fact, this is a necessary condition, all right, as well as being sufficient. All right, so it's pretty straightforward to see that it's a sufficient condition. You just write down what y, the output of the system, is in response to an input u, look at its magnitude, and then bound that by taking the absolute inside, okay, doing a change of variables, and you see that if you can bound this by a constant for all time, then you can bound the output in terms of that constant times the integral of the absolute value of the impulse response over time. So if that's finite, then the output must also be finite for all time. But it turns out also to be a necessary condition, and that's what these notes were about. Okay, it showed that we could construct a signal u, an input, that is bounded for all time, because it's either +1 or -1. It just takes the sign of the impulse response at a corresponding time, all right? And we saw that when you put that input into the system, the output turns out to be the integral of the absolute value of the impulse response up to that time, okay? And so if we can take that time up to infinity and still get a finite number, then that's telling us, well, the fact that our output is bounded for all time tells us we can take that up to infinity and still end up with a finite number. And so this condition is also necessary. So if you know that all bounded inputs lead to bounded outputs, then necessarily the impulse response is absolutely integrable. And the last little bit of written notes had to do with the comment at the end of this page, which is about marginal stability. I don't like to think in those terms. As soon as you've got a pole on the imaginary axis, whether it's repeated or not, it's unstable from the perspective of bounded inputs leading to bounded outputs. And we saw by example that if we just have an integrator, so that's one pole at s equals 0, if we put a step in, okay, which is bounded for all time, the output is not bounded for all time. It just ramps up and continues to grow. All right? So in order for the system to be stable, we need all of the poles to be strictly in the left half plane. As soon as we've got a pole on the imaginary axis or the right half plane, the impulse response will no longer be absolutely integrable. All right. There was this material, which is about the response of a system with a stable transfer function to sinusoidal inputs. Okay. In effect, we saw by this analysis that sinusoidal signals are invariants for systems with stable transfer functions. Okay, that followed by just saying, well, if we've got a stable transfer function and we put into it a sinusoid, which has Laplace transform as shown here, we get our output signal. We can do the partial fraction expansion thing that we did previously to identify components of the response to a sinusoidal input. Because the system is stable, all of these components of the response decay to zero as time goes to infinity by virtue of all of the poles being strictly in the left half plane. So all of these exponential terms will have, a negative real part for alpha here, which causes them to decay to zero. And you're left with, in the end, just this component here, which corresponds to this part of the partial fraction expansion. Okay, and these notes here were just about showing how you get that residue for this component. All right, and we noted that when the input has zero frequency, which is just like saying there's a step, then that tells us that in steady state we'll get a step out. Okay, and the magnitude of the step out that we get in steady state after all of the transient has expired will have magnitude equal to the transfer function evaluated at s equals 0. Okay. I know I'm going through this quickly, but we did have the lecture on Tuesday. I'm just trying to get a record of all the handwritten stuff. Okay. So we left off at the end of the lecture on Tuesday building up some intuition around the role of zeros of a transfer function in the response of the system to a step input. Okay, so all of this previous analysis told us that that the poles tell us about the components of the impulse response. Okay, and where the poles lie in the complex plane determines whether or not those components grow or decay as time goes to infinity. So the poles tell you, like in this example here, for the response to a sinusoidal input, how long it takes for the transients to expire before we reach steady state. But it doesn't tell you about what's happening during the transient part. It flicked to being connected. Yep. But to make that happen, I had to flick it to VGA and then back HDMI. Just plugging it in, it said it was disconnected. So I don't know why. Yeah, okay. For the first 4 weeks, I just plug it in and it would work. Yeah, okay. So I'll come back to do more testing. Yeah, at the end of the lecture. Yeah, okay. I'll hang around. Yeah. Yeah. All right. 5:15. Okay, I'll come back. Okay. Thank you. Thank you. All right. Sorry about that. So just knowing about the poles just tells you how long it will take to reach here. And that's really determined by the dominant pole, the one that's closest to the imaginary axis. That's the one that gives rise to a component of the impulse response that takes the most amount of time to decay to zero, leaving you just with the steady state part of the response. So to figure out what's happening during the transient part, we need to know how all of the components are being put together, right? And that's determined by the residues, okay, in the partial fraction expansion. Of course, they depend on the whole transfer function, all right, including the zeros. And so we left off looking at this example of a system that has a zero at s equals c, okay. For different values of c, we looked at the step response, okay. So the step response for a system with this transfer function, which is stable, okay, because it has both of its poles in the left half plane, will be a step out in steady state, and the value of the magnitude of the output in steady state will be equal to G evaluated at S equals 0. At S equals 0, this thing is equal to 1. All right, so that's why all of these, for all values of C, in steady state, it goes to 1. Okay, but you can see that for different values of C, you end up with very different transient parts of the response. When C is a positive number, which makes the 0 in the right half plane, you always get what's called undershoot in the transient part of the response. Undershoot corresponds to initially moving away from where you end up in steady state. Okay, that's why it's called undershoot. So it's about moving in the direction opposite to where you will end up in steady state. And we saw that the closer that 0 is to the imaginary axis, the bigger the undershoot. As the 0 moved this way, by increasing C, you get less and less undershoot. Even when C is equal to 10, there's a tiny little bit of undershoot here that you can't see. So it looks like zeros in the right half plane have this effect on the transient. They make you move in the wrong direction initially. Okay. On the other hand, when C is a negative number, okay, which will place the 0 in the left half plane, when that 0 is closer to the imaginary axis than the dominant pole, you get overshoot in the transient part of the response. So initially, it ends up going past where it ends up. That's why it's called overshoot. You go past where you end up in steady state. Okay? But as we move that 0 further to the left, okay, we get less undershoot. And once it goes to the other side of the dominant pole, you don't get any overshoot at all. Okay? So this is just an example. We're using it to build some intuition about the influence of the zeros of a transfer function on the transient part of the response. Okay? You can see here that it has a big effect depending on where it is. Okay, so here's some now analysis, okay, that confirms that intuition. Right? There's only so far you can go with intuition. The point of using mathematics is to draw concrete conclusions about things. Okay, so now we have the intuition. Let's try to do some analysis to understand how much undershoot a right half plane 0 results in. Okay? So let's take a situation where we've got a stable transfer function. So that says that the step response will reach a steady constant value eventually. Okay? How long it takes to reach that steady state is determined by the dominant pole. Okay? The one that's closest to the imaginary axis. And the so-called settling time will be about 5 time constants. All right? And the time constant associated with the dominant pole is just 1 divided by the magnitude of that pole. All right? So that's what TS is here. It's how long it takes for the transient part of the response to decay. That's determined primarily by the dominant pole. Okay? And we're saying that this transfer function at S equals 0 equals 1, so we know that the steady state output will have value 1. Okay, that's consistent with the analysis that we saw before. And we're saying that it has a 0 at S equals C, and we're saying that C is a positive number. Okay, this is really just defining the settling time. It's saying, well, after that time, the transient part has more or less decayed to 0, and we're just left with the steady state part. So in this situation, we see that some analysis, which is shown here, leads to a lower bound on the amount of undershoot. Okay? bearing in mind that we've normalised the steady state value to be 1. Okay, so we can think of this as percentage undershoot, right, when looked at as a fraction of 1. And so that lower bound depends on the location of the 0. All right? And in particular, it depends on the location of the 0 relative to the dominant pole. Right? So if we say that TS is 5 divided by the magnitude of the dominant pole, okay, so if C divided by alpha is still a small number, okay, then 1 divided by that will be a large number. Okay, so how can this be a small number? Well, we need to have on the imaginary, in the complex plane, if this is our dominant pole, okay, we need the 0 to be closer to the imaginary axis on the other side. Okay, if that's the case, this will be a small number and we'll get a large undershoot. That's consistent with the intuition built through this example. All right. Now, how do we get this result? Well, it follows from this analysis. Okay, it looks more complicated than it is. All right, so let me just explain it quickly. Rather than analysing the signal y directly, we're going to analyse a related signal called v. And that related signal is just 1 minus y. So if y looks like this, exhibiting undershoot and then reaching a steady value, v will look like this and reach a steady value of 0. Okay? By thinking about this signal, we can identify that after time t, the signal is bounded by delta. Okay? Where delta is just some small value. Okay? That's how we're determining whether or not the transient part has expired, right? Because if it's wiggling around close to its steady state value, we're just saying, well, it's at its steady state value. The transients have expired. Okay? And we have an upper bound for the signal. Okay? Now, we've defined this object. We can take its Laplace transform. Okay? The Laplace transform of V, right, will be Vs. It'll equal the Laplace transform of 1, which is 1 on S, and the Laplace transform of y. Well, the Laplace transform of y is just the transfer function g of s times the Laplace transform of a step. Okay, so taking the common factor 1 on s out, we see that the Laplace transform of this signal v is equal to the expression shown here. Okay. Now, by definition of the Laplace transform, we know that Vs is equal to the integral from 0 to infinity of Vt times e to the minus st dt. So if I evaluate that at s equals c, right, which is a complex number in the right half plane, that'll be part of the region of convergence for V, because V is a signal, right, for which I can find an exponentially decaying bound. And we saw from the analysis before that if we can fit our signal inside an exponentially decaying envelope, then all points in the right half plane will be in the region of convergence. In fact, the imaginary axis will be in the region of convergence. We can push it into the left half plane. Okay, so that's a valid thing to write down. Okay, and if I evaluate this at s equals c, what do you get? You get 1 minus g at c, which is 0. Okay, so 1 times 1 on c. So it's just 1 on c. Okay, now let's split this integral into two parts, into a part up to this time and then a part after that time. Okay, so that's what's happening here. It's just being split into the two parts. And now to get to here, we replace this object by its upper bound. Okay, so if I now integrate this up to time t, I'll get all of that area, which is going to be greater than integrating this object, even when you've weighted it by an exponentially decaying thing, right? Which is why this becomes, this is an upper bound for this. all right? And then this guy here, we can replace by this upper bound by using the fact that in here, the signal wiggles between plus and minus delta. Okay? Now, you can evaluate these integrals explicitly because we're just integrating an exponential function. We know how to do that. All right? And this is what you end up with. Now, manipulating this, right? So really we're saying 1 on C is less than or equal to this guy here. All right? So the common factor C can be cancelled out, which gives you this. All right? And following these steps is just about algebra. Okay, so if I, multiply, take that over to the other side and multiply that, take that over to the other side, that gives me this term here, divide by that factor there, and then take the 1 over to the other side, that gives me this. Okay, so we can see that this analysis has led to a lower bound on the percentage undershoot. All right, and this is now just rewriting the lower bound in a different way to give us this expression here. Okay, and to get to this approximation, we're saying, well, e to the CTS for small CTS will be 1 plus CTS. And then that 1 cancels with that 1, and you're just left with that. Okay? So, it's always good to follow up intuition with a bit of analysis. Okay? So, our example said, well, if the 0 is close to the imaginary axis, much closer than the dominant pole, I get a lot of undershoot. Okay? And that is consistent with what this analysis is telling you, on the understanding that TS is like 5 divided by the magnitude of the dominant pole. So in this case, it's 1. Right? So as long as C is less than 0.2, this will be a small number, and I'm getting a lot of undershoot. It's a lower bound. You could do this analysis even if there were multiple zeros in the right half plane. You could do the same analysis. There wasn't anything special about the particular C that I chose, other than it makes the transfer function equal to 0. Right? The one that will give the biggest lower bound here is the one that matters most. Okay? And that will be the one that's closest to the imaginary axis. Okay? So, what dominates undershoot is the 0 in the right half plane, if there are any, that is closest to the imaginary axis. Just like how long it takes to reach steady state is mainly determined by the pole that's closest to the imaginary axis. So you can do similar analysis, which we won't go through in detail, to understand how much overshoot you get when the 0 is in the left half plane, okay, but closer to the imaginary axis than the dominant pole. So our example suggested that in that case you would get overshoot, whereas when the 0 is on the other side, you don't get the overshoot. Right? But you can do similar analysis of a signal that looks like this. I'm just drawing in what this means. Right? It's a little envelope that we can really put around the part of the response after the settling time. And all of that information can be used to arrive at a lower bound for the amount of overshoot. Okay? And again, by looking at this lower bound, you see when the product of C and TS is small, meaning this guy is closer to the imaginary axis than the dominant pole, you will get a large number here, okay, which means the overshoot will be large. Okay, the closer this guy gets to here, all right, this bound goes to 0. All right, and so you don't necessarily get overshoot in that case, which is consistent with the intuition that we saw here, that for small values of C, you get overshoot, but as you keep increasing C, you end up with no overshoot at all. Okay? The analysis is very similar to this, and if you're interested, you can go and look in the Goodwin book. All right? But the point of showing you this in detail is to make you believe in analysis, if you like, right? It's informative. It tells you something, and you shouldn't be scared of it. It's not as complicated as it looks. Okay? It just involves drawing some pictures sometimes and then putting information together to draw a conclusion. Okay? All right. So in the rest of the lecture today, I want to look at frequency response. So we've already seen on page 42 that if we put a sinusoid in, and remember complex exponentials can represent sinusoidal signals, okay? E to the j omega t is just something that whizzes around the unit circle. How fast it whizzes around the unit circle is determined by omega. The bigger omega, the faster it whizzes around the unit circle. If we project points on the unit circle onto the real axis, okay, then we'll get a signal going backwards and forwards like this, oscillating like a sinusoid. If we project it onto the imaginary axis, we get something oscillating like this as e to the j omega goes around the circle, just like a sinusoid. So we're using these to represent sinusoidal signals. And the analysis we started off with in the lecture today to cover off things discussed on Tuesday suggests that, well, if we wait for all of the transients to expire and just look at the steady state part of the response, then that will be another sinusoid of the same frequency, but scaled in magnitude by the magnitude of the transfer function evaluated at s equals j omega, and shifted in phase by the phase of the transfer function evaluated at s equals j omega. Right? Remember that the transfer function is the Laplace transform of the impulse response, okay? And like all Laplace transforms, it's a complex number, right? So for all values of s, it has a magnitude and a phase, okay? And when we evaluated s equals j omega, it's telling us how big the magnitude is telling us how big the sinusoid we get out in steady state will be, right? And the phase tells us how much it shifts in phase relative to what went in, okay? So the thing to bear in mind here is that this so-called frequency response is a complex number, all right? It has magnitude and phase. Alternatively, you can think of it in terms of having a real part and an imaginary part. Okay, but most of the time, because of this result, we think in terms of its magnitude and phase. And that's precisely what we draw in Bode plots. Okay? We'll get to those in a minute. So this is just an example, all right, where we've got a system that has a stable pole at s equals minus 0.5, that's what makes the denominator here equal to 0. So this system will reach a steady state when we put a sinusoid in, all right? But before the steady state, there's a transient part of the response, okay? We're saying let's put a sinusoid in as a pure sinusoid rather than something that's represented by a complex exponential. The Laplace transform of a signal that looks like this is like this, okay? The output will have Laplace transform equal to the product of the transfer function and the Laplace transform of the sinusoidal input, okay? The inverse Laplace transform of this will be what the signal looks like at the output in the time domain, and there will be two components. There will be a transient part and a steady state part. Because the system is stable, the transient part goes to 0 as time goes to infinity, as we saw in the preceding analysis. And what we're left with in steady state is a sinusoid of the same frequency as the sinusoid that went in, scaled in magnitude and shifted in phase. Okay, so the blue curve here is what went in. Okay, so it's a sinusoid with frequency 5. Okay, 5 radians per second. And the red curve is what comes out. So you can see that eventually we end up with a sinusoid. It has the same frequency. The distance between these peaks is the same as the distance between these peaks. That's how you tell that it's the same frequency. If it's the same frequency, it has the same period. Okay? But before that time, there's a part that consists of the transient response, right? Plus a sinusoid, which is why it doesn't look like a sinusoid. It looks like a sinusoid that's got something that's decaying, right, to leave us just with the sinusoid. So back here we've got the sinusoid plus something that's decaying, which is why it lifts up a bit here and goes down before we reach the steady state. Okay? You can see that the magnitude of the sinusoid out is smaller than the magnitude of the sinusoid that goes in, which is 1. Right? And sure enough, if you evaluate the transfer function at s equals j times 5 and take the magnitude, you get this number here, which is less than 1. Okay? How much it shifts in phase is given by the phase of the transfer function evaluated at s equals j5. Okay? And that will correspond to a shift in time by that number divided by 5, right? Because if I've got sine 5t plus angle g j5, that's equal to sine 5 outside of t plus g j5 divided by 5, right? So that's how much it shifts in time, okay? And, you know, if you go and measure what that is, it is precisely the angle of the transfer function evaluated at s equals j5 divided by 5. Okay? You get a negative number here, right? Which tells you that the output sinusoid lags the input sinusoid. Okay? You can see that you're getting this peak here because there was a peak in the input sometime in the past, this amount of time in the past. Okay, so when you get a negative number here, it lags. Sometimes, for some transfer functions, you'll get a positive number here, and that will be leading. And so you'll get a peak in the output, okay, that comes before the peak in the input. All right? So it's useful to think in terms of frequency response. Okay, it tells you a lot about a system. Before I talk about that, which is really based on the fact that lots of signals can be thought of in terms of how their energy is distributed across frequency, let's think about, for a minute, how we can represent the so-called frequency response in terms of its magnitude in phase on a plot, something called a Bode plot. Okay, so you've already played with these sorts of things in Workshop 1, where you used MATLAB to produce a bunch of frequency response plots. Okay? Yeah, and you should have observed that transfer functions like this have a magnitude plot when drawn on a log scale that looks flat at low frequencies and then rolls down at high frequencies. And you should have noted that where it breaks is related to the location of the pole. Okay, you should have observed that the phase plotted on a linear log scale for a function that has a pole in the left half plane is something that starts at 0 degrees and goes to minus 90 degrees. Okay, we often plot these things in radians as well, so it would go from 0 to minus pi on 2. All right, scaling the gain doesn't do anything to the phase. All right, assuming that k is a real number, right? Because the phase of a real number is 0, and that gets added to the phase of the rest of it. So it doesn't change the phase, but it will change where it lies on the magnitude part of the plot. All right? You should have seen for second order systems that you can get these so-called resonances in the response depending on what the damping is. And that now the phase, as we range across all frequencies, goes from 0 to minus pi, because there are two poles. Okay, zeros make the magnitude plot kick up. All right, makes the phase move in a positive direction rather than a negative direction if they are in the left half plane. Okay, so what we're going to look at now is how to get a feeling for what these look like when you haven't got a computer in front of you. So you can always just chuck this into MATLAB and it'll spit out what the response looks like. When you're doing design, you often want to know how adding zeros and poles to a transfer function will change the Bode plot. Okay? And the reason for drawing the magnitude part on a log scale and the phase part on a linear log scale should be clear from this. Okay? So if we're given a transfer function, okay, which is a real rational transfer function, the ratio of two polynomials, and we factor those, factorise those polynomials into a products of degree 1 polynomials on the top and the bottom, okay, and look at the magnitude of this. So the magnitude of this will just be equal to the magnitude of this times the magnitude of this plus the magnitude of all the other ones divided by the magnitude of this, and so on. Okay? And we know by properties of the log that once we take the log of the magnitude, then we'll end up with this sum. Okay? There will be a sum due to the gain k here. There will be a component in this sum due to each of the zeros, okay, in this form here. And there will be a component in this sum that relates to each of the poles corresponding to these components here. All right, so we can think about the magnitude part of the so-called Bode plot, so this guy, this guy, this guy, this guy, in terms of a sum of components. And these components have a simple form. So once you've understood what the magnitude plot of this looks like, you know, you can just add them together to similar terms to construct the overall magnitude plot. Phase, okay, naturally decomposes into a sum, okay, without taking the log, right? So really the property that we're using here is that given two complex numbers, the log of A times B is equal to the log of A plus the log of B. That's just a property of the log function, okay? And if I've got two complex numbers A and B and I look at the phase of their product, then that's just the sum of the phases. Okay? So if we can figure out what the Bode plots of simple functions looks like, then we can build the Bode plot for a complicated function by just adding them together. All right, so that's the basic idea. So let's look at what the Bode plots of these simple functions might look like. So let's look at a function that looks like s plus 1, or ts plus 1, in this case with t equal to 0.1. Now let's think about what we're drawing here. We're looking at not doing this for any value of s, but we're looking at doing this for s equals j omega, as omega goes from 0 up to plus infinity. Okay? So we're evaluating these functions along the imaginary axis. Okay? So let's look at what s plus 1 looks like for values of s along the imaginary axis. Okay, so s will be this vector here. Okay, remember complex numbers are just vectors in the plane, right? The real part is what we draw along the x-axis and the imaginary part is what we draw on the y-axis. All right, so if I'm evaluating S at a point, this point on the imaginary axis, then I should think of S like this little vector. All right, and I'm adding to that vector 1, which is this vector. Right, how do you add vectors together? Well, you just add them together, right, head to tail, and then get the result. Okay, so this point here is S plus 1. All right. Another way to look at what that number is to shift the origin to the value that makes the function 0. Right? So if I shift the origin to -1, which makes that 0, and draw a line up to S, I get the same vector. Right? Now the thing I'm interested in plotting in the magnitude plot and the phase plot is the magnitude, why doesn't that show up? Magnitude of this vector and the phase. The magnitude is the length and the phase is the angle. So I can do that with this vector, measure its length and its phase. And that's really all we're plotting on the Bode plot, okay, for simple functions like this. So that's what this picture here represents, okay? So I'm now looking at the vector from the value of S that makes that equal to 0 and drawing that to the corresponding point on the imaginary axis. So this is what I get when S is equal to j omega 1. This is what I get for S equals j omega 2 and so forth. Okay? Now what can you notice about the magnitude of these things? Well, initially the magnitude is 1. Okay? So when S is equal to 0, I just get this vector here which has magnitude 1. If I take the log of 1, I get 0. So for small frequencies, you know, the magnitude's not much different from 1. And so from small frequencies you see that you're stuck on this so-called 0 dB line, right? So 0 dB corresponds to 1, right? Because it's the log, 0 is the log of 1. Okay? Now as you increase omega, the length of these vectors gets bigger and bigger and bigger. Okay? So once we go past 1 here, okay, so when we're at omega equals 1, right, we'll get a triangle like this, where that's 1, and this will be root 2. Okay? So when we reach a frequency that's consistent with the anchor point for this function, the value of S that makes it equal to 0, you can see that we're no longer looking at a vector with magnitude 1, we're looking at a vector with magnitude root 2. Root 2 is 1.4, you take log of that, it's still pretty close to 0. And if you multiply it by 20, you'll get 3 dB. So at the frequency corresponding to the 0 location, all right, it's obviously going to start getting bigger, but it won't be much bigger than 0 dB. It'll be sitting around 3 dB. Once we go past this frequency, okay, we're looking at vectors. If we go well past that frequency, we're looking at vectors that are getting very big, right? And the length here will be approximately equal to the length there, because it'll be much bigger than this length here, which is always 1. Okay, and so we can approximate that by saying the length here is approximately omega for big omega. All right? And in dB, we just take the log of that. All right? And if we're plotting along a log scale on the x-axis here, then you can see that for large omega, this behaves just like a straight line. So as a function of log omega, it's just a straight line with a slope of 20. Right? And every time this increases by 10, we will go up by 20. Right? So for every decade, we go up by 20. Right? Where it kicks up is determined by the location of the 0 of that function. Okay? Now, if the 0 moves, like in this guy here, right, that's saying that the 0 is now sitting at s equals minus 10. So for this approximation to become good, we have to go past 10, right? Up to that frequency, we're still pretty close to 1, because root 2 is still close to 1. All right? So we have to go further along the imaginary axis in order to start moving away from the 0 dB line. Okay? But once we go past this point, you're again looking at these big vectors with magnitude that's approximately equal to how far along the imaginary axis you've gone. Right? And again, it starts going up at 20 dB per decade. All right? Now, look at what the phase does. What does the phase do? Well, it starts off at 0. What's the angle there? It's 0, right? And it starts increasing. Okay? And when if that's 1 and that's 1, then we'll have a phase of 45 degrees, which is pi on 4. All right? And then eventually, when we've got these big vectors that are going up to a really large frequency, what angle is it approaching? It's approaching a right angle, which is pi on 2. So when we hit the frequency that's as far up the imaginary axis as the 0, okay, then we will be at a frequency of 45, okay, and eventually that'll keep going until we get to pi on 2. All right? If the 0 is further that way, like in this picture here, we have to go up to 10 to get an angle of pi on 4. Okay? So that's why the frequency at which it's pi on 4 for this guy here is further to the right. Okay? Now, these functions here are just the reciprocal of these functions here. And we know that the magnitude of 1 on a complex number is just 1 divided by, what's happened to my pen? The magnitude of that number. Okay? And the log of 1 on a number is just minus log of that number. All right? And so you see that what happens is that these guys just get flipped in the x-axis. So here's the 0 dB line. These ones went up, right? But these ones go down. These ones go up, it's always positive. These ones are down, negative, because we've got this minus sign here. Right? Where it kicks down depends on the value of s that makes the denominator 0. In the same way as where it kicked up, I don't know why this is not working, depended on the value that made this function equal to 0. All right? So the value of s that makes, if it's the value of s that makes this equal to 0 is further to the right. It takes longer in terms of how far you have to go up the imaginary axis before it kicks down, just like here. It took longer before it kicked up. Right? The phase of 1 on A is just minus the phase of A. So again, the phase parts of the plot just flip around. Okay, here we were starting at 0 and went up to pi on 2. Now we start at 0 and go to minus pi on 2. Okay. Now these functions were such that the value of s that makes the numerator here, or the denominator, was in the left half plane. Okay? When it's in the right half plane, the little vectors that we're drawing just go from the right half plane instead of from the left half plane. Okay? So the magnitude of these vectors behaves in the same way as the magnitude of these vectors as we increase frequency. So the magnitude plots look the same. What changes when you're dealing with a factor that corresponds to a zero or a pole in the right half plane is the phase. Okay, you can see here that the phase when we've got omega equals 0 is this angle here. Right? What's that angle? That angle is pi. Right? And what happens as we go to a higher frequency is we get a smaller angle. Right? So we start at pi and it moves down to pi on 2. Right? As omega goes to infinity, it's like we're looking at an angle that's just a right angle. Okay? Which is why it ends up going to pi on 2. Whereas when the 0 is in the left half plane, okay, it started off at an angle of 0 and it increased to an angle of pi on 2. All right? And the same sort of thing happens for the pole. Again, this is just the mirror image of these things in the x-axis. So now we know what each of these terms will look like. Right? This thing doesn't depend on s, and so it won't depend on omega when we evaluate s at j omega. So it just is a constant value for all frequencies. Okay? So let's look just quickly at a little example of putting all of these things together. Now, it's sometimes convenient to rewrite this with the factors expressed like time constants. Okay? So let me take a factor of 5 out the front of the top bit. So we get 0.2s plus 1, right? And take a factor 10 out the front here and get 0.1s plus 1. Okay? Now, the magnitude plot, which is what we're drawing here, okay, will consist of 1, 2, 3, 4 parts. Okay? Let's start with this guy here. Right? That's something that is just, when s is equal to j omega, is 1 on j omega. Right? We're going to take the magnitude of that, which is just 1 on omega. Right? And then we're going to take the log of that, right? Which is going to give us minus log omega. Okay? So that's going to be a line with slope minus 20 when we multiply by 20 to get it into dB. And it will be equal to 1 when omega is equal to 1. So we're going to get a line on the Bode plot that looks like this. Okay? That'll be at 0 dB when omega equals 1. It'll be at minus 20 dB when omega equals 10. And it'll be equal to 20 dB when omega equals 0.1. Okay? Now let's look at this term. This term is 0.5. If we do 20 log 0.5, then that's approximately equal to minus 6. Okay? So we'll get a component that's just a line across here, like this. Okay? And that's that term there. This guy here will be something that's 0 dB, right, until we get to s equals a frequency that makes, that corresponds to this number here, and then it will kick up, and it will kick up at 20 dB per decade, right? This guy here will be something that is 0 until we get to 10, right? And then it'll kick down at 20 dB per decade. To get the total, right, we have to add all of these things together. And so the total, remember that we've got this line here as well, the total will bring, 0 doesn't add anything. So initially we've just got this minus this, so we end up with something that's slightly lower, right? It'll follow this all the way down until we get to this frequency here. Then it will come up again. It'll flatten off because we've got something going down and up at the same rate, and then it'll kick down again. Okay? And there you have the total magnitude plot. The thing to realise here is that it's just the sum of this guy, right? This guy here, which is the one on S, this guy here, which is this factor here, and this guy here. And you just